So I'm going to start recording and yeah, get into some intros. I'm really excited to introduce our panelists for today's guest talk. We have three wonderful people joining us to share more about climate AI and machine learning applications. We have Davitt from ClimateTRACE. You can wave so we know which one you are. I guess you can see Aaron. Yeah, there he is. And Aaron received his BA degree in ecology from the University of Denver in 2006, a master's in geology from City College of New York in 2011, and received his doctorate from the City University of New York Graduate Center last month. His previous research focused on the application of optical infrared Landsat 8, thermal infrared eco-stress, and microwave remote sensing data to inform on crop growth and flood monitoring and modeling of crop canopies. And his current position is at WattTime as the principal analyst in remote sensing, where he helps identify satellite data sets for use in the ClimateTRACE coalition efforts to improve greenhouse gas monitoring. Welcome, Aaron. And Gopal is serving. Sorry, what was that? Oh, sorry, just some background noise. Gopal, do you want to give us a wave so we see you up there in the, there's Gopal. He is the CTO and head of product at Sust Global, focused on geospatial analysis or analytics for climate adaptation. And most recently, he led the analytics engineering team at Planet Labs, an integrated aerospace and data analytics company that operates history's largest commercial fleet of Earth observation satellites. Planet Analytics serves a range of customers from city planning teams in governments and the World Bank to defense and intelligence functions across the world. He is known for agile engineering execution from concept to scalable, high-quality products. He has been an invited speaker at global industry conferences like Google Cloud Next and leading technical conferences in the machine learning space, such as ICML and CVPR. Gopal holds a master's in electrical engineering from University of Southern California and completed the Ignite program, connecting technologists with new commercial ventures at the Stanford Graduate School of Business. And Anthony, let's see, I'm looking at my screen here too. There's Anthony, beautiful background up there, is head of product and growth at Climate.Ai. He has over 10 years experience commercializing technology at the intersection of science and technology and multispectral imaging and analytics. He is the co-founder of the Stanford Alumni in Food and Ag group and a mentor with Techstars Farm to Fork Accelerator. He is a Stanford alum and first place winner in an international science and engineering fair. And yeah, we are just so lucky to have this group of panelists here today. So I was not planning any particular order for each panelist is going to share briefly in 10 to 12 minutes their work and their what they're up to, and then we're going to leave plenty of time, about 25-30 minutes for open Q&A and discussion. So let's start with you, Aaron.
All right. Well, thank you for having me. Let me get my share screen going. All right. Can everyone see the screen here?
Yeah.
Great. Okay. And if there's an issue, just yell, because we all know how problematic Zoom can be. So, all right. Yes, thank you for the introduction. My name is Aaron Davitt. I am principal analyst of remote sensing at WattTime, which is part of a bigger coalition called ClimateTRACE, which stands for Tracking Real-Time Atmospheric Carbon Emissions. So what I'm going to do is give you a sense of what ClimateTRACE is this coalition, but also the role I play in it. And let me see. All right. Sorry. There we go. All right. So what is ClimateTRACE? It is an initiative launched by a coalition of organizations that will use artificial intelligence, satellite imagery, machine learning, and other technologies to monitor greenhouse gas emissions worldwide. Our mission is to make anthropogenic carbon emissions transparent, accessible, and actionable to the world's governments, NGOs, private sector, and citizens through collaborations with like-minded organizations. So this coalition, ClimateTRACE, was started with Wattime, Google AI, and Carbon Tracker. So it's a bottom-up creation of like-minded organizations and individuals that want to do good. And each member here that you can see with the images here, specialize in a specific sector. And when I mean sector, I'm talking about the transportation sector, construction, agriculture, and so on. So each of these members here monitor greenhouse gas emissions from that specific sector. So ClimateTRACE aims to launch a publicly accessible greenhouse gas emissions database in the summer 2021 that is global, comprehensive, real-time, empirical, and extensible. But the question is, why create this database? Well, just some of you may or may not know, currently in many countries and individual sectors, the state-of-the-art tool to monitor greenhouse gas emissions is still to ask emitters to self-report their own emissions. And then that information is manually compiled for the results. Consequently, many governments, companies, and scientists must rely on data that can be years out of date, sometimes subject to deliberate underreporting, and often only provides a high-level summary of information that lacks specific details. So the goal, or the mission of ClimateTRACE, is to cover all major greenhouse gas emitters sectors globally. And this is meaningful for a couple of reasons. First off, like I said, many countries, especially in the developing world, do not have access to technology or financial resources to be able to install greenhouse gas monitoring systems. And two, for many sectors, the greenhouse gas measurements are not sufficiently precise, and given the contextual nature of emissions from sectors. So ClimateTRACE aims to address this by providing data that will be available for all countries, regions, and by improving on the state of the art for emissions monitoring specific sectors. So here's the idea of the tools and technologies we will use to monitor greenhouse gas emissions. So the ClimateTRACE system incorporates different types of satellite imagery collected by various space agencies and organizations around the world. Then the AI machine learning can be trained to spot indicators of pollution and greenhouse gas emissions in the satellite imagery. This will be fed into a web-based database that will be accessible to the public. It'll be sortable in a variety of key breakdowns, including geography, sector, by source, etc. People will be able to generate reports and data sheets and then conduct an analysis from there. So although each coalition member covers a specific sector, all models will be based on some form of remote sensing data and ground truth data, analyzed through AI machine learning models to estimate greenhouse gas emissions, and it will be extended to regions without ground truth data. Now, just so you know, we are not doing an academic project. This is not just, crunching numbers and that's it, but we're trying to make a real difference with this tool, this information here. And we are working from a certain impact objective, as you can see here. And when I'm talking about impact objective, for example, I'm talking about building trust in the Paris Climate Treaty to have objective data on greenhouse gas emissions, but also helping developing countries have the tools needed to monitor greenhouse gas emissions to create some type of meaningful impact with these examples here. Now, right here, as you can see, is my specific job. The red box outlines the satellite data here. This is where I come in. I work on the satellite data side of the project. So I want to make it clear, with my experience, I am not a data scientist. I am a remote sensing scientist. And some of my previous work focused on flood and crop monitoring, which required combining satellite imagery, modeling, ground data. A lot of the time with my doctoral research, focus on this, but also how can satellite imagery be used individually and in combination to monitor land surface conditions. So taking this and by extension the ClimateTRACE, I'm trying to understand and inform to the data scientists how can satellite imagery be used to monitor greenhouse gas emissions. So really my role at Wattime is to leverage my remote sensing expertise to bridge the work of the coalition members and collaborators that have the highest impact on global greenhouse gas monitoring and reporting. With that, I work with the data scientists, policymakers, ground data experts, and like in a holistic approach to monitor emissions. And the images here kind of give you an idea of what my role entails. So here's an image of a power plant in Arizona. And what I do is identify different satellite imagery, as you can see here with EcoStress and ResourceSat-2. So this is a sensor mounted on the space station, and this is an Indian satellite that's been in orbit for a couple of years now. EcoStress measures land surface temperature, and ResourceSat measures different bands of the electromagnetic spectrum. In this case, we have red, green, and shortwave infrared imagery here. So the question is, how can we use these satellite images to spot indicators of pollution and greenhouse gas emissions from this coal power plant? Also, can this information gleaned from these satellite images be transferred to other locations? And can we use other satellite platforms to inform us emissions coming from this coal power plant or some indicators of emissions at this coal power plant? In addition to identifying satellite imagery that could be useful, I have to interact with the coalition members across different 8 organizations to understand their remote sensing needs and provide some advice on what to use. I do education efforts to explain the work and application of what we're trying to do, like with this presentation, this panel here. I field inquiries from the data scientists on how to improve algorithms related to remote sensing data. I perform my own. Sorry, question? Okay, I'll keep on going. Perform analysis. I also make informed decisions on purchases of satellite remote sensing data because not all of it's free out there. And like I said, communicate this information to data scientists. So looking back at my PhD and teaching career, I lean into the skills I developed over time and apply them to my current role. So here's another example of what I do. Here's some specific sector coverage for the 2 coalition members. We have here Blue Sky Analytics based in India, and they look at farm and forest fires. And we have Hypervine here based in the UK that look at emissions from construction and mining. And on the Venn diagram here, provides an example of what I try to do. So Blue Sky Analytics looks like crop burning. Watt Time looks at plume emissions from power plants. That's my organization. And Hypervine's looking at identifying mining type and emissions. So the question is, how can we use the same sensor to answer all 3 of these needs? And then I relay that information to data scientists and the AI folks, and also the coalition members, so we can decide, okay, we can focus on one satellite to answer all our needs. So some key takeaways. The ClimateTRACE Coalition requires different expertise to monitor greenhouse gas emissions. So being a data scientist is only one member of the team. So climate scientists, remote sensing scientists, engineers, and more all contribute to the team. So the skills required for my position, being a remote sensing scientist, is being familiar with various remote sensing platforms, and the application context is important. Understanding how the data will be used, what the data is measuring, and what data is needed to be useful. Also, experience with combining remote sensing, modeling, and ground data to answer a question. That's very useful experience. Communicating the data and application, especially in the context of the mission, and also being able to work with a team and translating across different groups between data scientists, policymakers, and then like my side, remote sensing folks. So thank you for your time. Appreciate you listening. So if you want more information, feel free to email me at aaron@wattime.org. And feel free to check out these websites here. This is the Wattime website, and here's the ClimateTRACE website to provide more information on what ClimateTRACE is doing. And you can follow us on Twitter. But also here's an article that was sent to Medium back in July talking about the launch of this coalition. So if you want some more information, the Medium article is a great resource to use. And also on the ClimateTRACE website, feel free to check for job postings. Everything. We are looking for data engineers, but there might be other positions that might be of interest to you. So thank you.
Thanks so much, Aaron. That's great. That's really super informative and wonderful to hear about. I'm sure if anyone has any burning questions that they want to bring up now, go ahead. We could maybe just take one if there's a big one. Otherwise, we'll go into the other two panelists and have an open Q&A at the end.
I'd love to ask a quick question if that's okay.
Of course.
I'm kind of curious about the kind of litigious side of all of this. Like, are you guys worried at all about kind of getting, sorry, I wrote notes and I'm losing them. Are you afraid of like these kind of big fossil fuel companies trying to like suppress your findings? Also, I'm just curious if you guys find any kind of illegal activity through this, or like activity that shouldn't be occurring or should be more regulated, but is occurring. But, yeah,
Okay.
does that make sense?
I'll answer your second question first before I get to the first one. So yeah, one of the things is we're trying to be an independent monitor of greenhouse gas emissions. So we're trying to be, well, we are being objective with this. So one of the things is tracking legal polluters or illegal activity. That is one of the goals, but that's only a small part too. Because initially when I entered this role, it's like, yeah, we're going to get those people that are harming the environment. But it's also, we realize too, there are also a lot of groups out there, companies and all, they're actually doing good. They're actually doing a good job reporting out emissions. So this is a way to support that, like, yeah, actually, you know, they're right in their estimates, and that helps with policy too, giving them some support that way. So a little bit going after like the legal, but more about supporting like the good actors in this.
Mm-hmm.
And the first one is, in terms of suppressing, we haven't encountered that, but also there seems to be a shift with some of the industry people we've talked to do a better job with tracking greenhouse gas emissions, because it seems to have reached a certain point where it's economically important to be much more transparent, but also considering the greenhouse gas emissions.
Mm. Thanks for that question and your response, Aaron. And we're going to move on to Gopal and Anthony. But Aaron, if you want to look at a few of these questions in the chat and answer some of them while they present, that's one option. And then any that don't get answered or that are longer explanations, we can come back to in the open Q&A. So let's see, Gopal, I will turn it over to you, and you should be able to share your screen and yeah, get right into things.
All right. Thank you for organizing this. I'm gonna try and share screen. Is it showing up?
Yeah.
It is. I see you nodding. Wonderful. All right. Good morning, good evening, everyone. Seems like we have folks joining from all over the world here. So super excited to be presenting to you all and sharing some of our hard-earned wisdom on some of these climate-related topics to all of you, and excited to engage with this community. Thank you, Aaron, for your presentation. It touched on a few of the things I've lived through in my past life around sensor modalities and bringing data together towards having meaningful insights. So I want to tell you a little bit about planetary scale location insights and how that connects into climate adaptation. Seems like all of you have come together with a common purpose around climate change and your interest in climate change. So I wanted to share some knowledge there and, you know, hear your thoughts through this process too. So I serve as the CTO and head of product for a new venture, Sust Global, where we focus on global sustainability of operations in the context of the ever-evolving climate. And our company is being founded with the mission to democratize access to climate data and make the world's climate data universally accessible and actionable. So, you know, in just to give you a quick background, I've spent the better part of the last 15 years working on different aspects of spatiotemporal data. I spent a lot of time on imagery. I was part of the founding team building Dolby Vision, which is like a product in the cinematic space, and since then transitioned into more environmental data, working at Harvesting and Planet in the last few years. I was the head of analytics and insights at Planet, where we were responsible for bringing out some of the data-driven insights from the rich collection of Earth observation data sets that Planet collects. And now I work on this new venture. I've had the fortune to share some of this work in some interesting venues in the past. I just want to talk about climate adaptation real quick and how we look at this space. So, you've probably heard a lot about the climate models, and in the broader context, you can think of it in the context of space and time. And most climate models have uncertainty in some form. And that kind of affects decision making based on climate, as you'll see from a few examples I wanna share with you. That's temporal uncertainty and positional uncertainty. And when you look at most global climate models, they cover the historic, they cover the future, they go from today to the end of the century. And the challenge there is often the positional uncertainty, which is how accurately over like a specific region can you understand the effects of climate. And what we have learned in the last few years is when it comes to policy, when it comes to decision making that happens at a local level, whether it's climate adaptation or climate mitigation, and climate models go very global, and which is great, but they are often challenging to make actionable decisions based on. So in order to bridge these two worlds between climate models and business decision making, you kind of need to be able to bring together the knowledge of the environment and the changing climate at asset level. And that's what we call asset level geospatial analytics. So bridging the void between climate models and actionable decisions. So I want to talk about, take a step back and talk about imagery analytics for location insights. I felt like many of you folks are like, in regions where there's been increasing amount of flooding, be it India, Bangladesh, parts of Europe, where there's a 1 in 100 severe year floods severities that are impacting regions in successive years, which normally shouldn't happen. So I want to just talk about how you can do some analysis at the asset level in this context. So talking about the work we did at Planet, like here is an indication of the Dow satellite. At Planet, we have upwards of 150 of them in orbit. Some of you are curious about resolution. It's probably 4 to 6 meters, depending on the latitude you're at. And in terms of ground sampling distance, with an orbiting altitude of like close to 500 kilometers. And that, through having many satellites, we're able to create fairly rich mosaics which have fairly good coverage at like a monthly or an annual cadence. So think of it as like through these satellite data captures on Earth observation, you're able to get to something like a Google Earth every week or every month. So through that, we can find changing patterns of human settlement. This is some work we did around bridging the gap between data science, the geospatial data, and what's actionable intel. This is a map of all the roads and buildings across the world in 2019, which was mapped running some machine learning algorithms on top of the monthly and seasonal mosaics from Planet's data. So one of the things we looked at in terms of urban growth is over the course of a study period of 18 months, how do cities really evolve and which parts of that city fall under flood risk regions. And that's kind of the kind of data that civil governments, city planning officials are often craving for, because not everywhere is there like a consistent way of doing census and understanding patterns of growth. So this is kind of the rough workflow. You go from imagery to monthly building maps, and then from the building maps over successive months, you can identify changes of building growth, which is indicative of changes in human settlement and how they intersect with flood risk, and what are the hotspots which are vulnerable to floods. So that's a high-level idea. We looked at 5 cities. And I just wanted to show you examples of like imagery related to this. So one of the cities we studied was Baingui in the Central African Republic. And this is kind of what the mosaic looks like. So if you look at October 2017, this is what the city looks like from overhead imagery at like 4 to 6 meter resolution. And I'm going to just flip through a few images in successive months. and show you kind of what roughly we can see as like patterns of growth. So this is what it looks like in the beginning of 2018. This is April 2018. This is like mid 2018. And you can see over the course of months, you kind of see an expansion westwards of the city. And then if you run the machine learning or AI capability on top of this imagery to detect buildings, this is kind of what it looks like in the first month. This is kind of what it looks like in the last month of the study. That's 18 months apart. So this is at the beginning of the study. This is at the end of the study. And through that, you can identify the hotspots of built up area. And the hue of like the yellow here is indicative of like the increased amount of building density in a specific region around the city. So this is indicative of the kind of patterns of growth in most African cities, because the growth is more lateral rather than vertical, like what you see in like a Dubai or like San Francisco or any of the developed cities. In Africa, it's more lateral, and the city expands kind of outwards. And you can see that in this city as well. It's one of the fastest growing cities in Africa. And if you overlay a flood risk map, this is kind of what it looks like. So what you see in red are indicative of areas with very high flood risk. So ideally, you don't want a lot of human settlement there. But then this kind of begs the question, which is, where are we building, and are we building consciously? And that's kind of the question you can answer with this. So you can identify hotspots like the one highlighted here. So then you can quantify that risk, which is between the period of the study, how much of growth has existed, and what percentage of that growth is in high risk areas in specific cities. And that's kind of the capability we were serving city planning teams across the world, including the UN building development team. So that's one case study. I want to tell you about another interesting one around wildfires. So no conversation in Northern California, especially in the parts of the world where I'm at, which is in San Francisco, is kind of like relevant if you don't talk about wildfires, because that's what we've seen the most of in this year. So just to take a step back and look at climate models, this is kind of what an Earth system model predicts in the context of warming temperature between the beginning of the Industrial Revolution. I think that's how they pick 1850, and the close of this century. And you've seen some version of this figure in any textbook around climate change. But what this tells you is, across different scenarios, what does the average lift in terms of warming temperatures look like across these scenarios, which are called the SSPs and the representative concentration pathways. So together they kind of model the social and economical dynamics across the world and how that connects into climate change and warming in different parts of the world. So this is kind of like across the world, the warming graph, and you can see the variability based on the scenario. So if we as like a society do the right thing, and the right thing is essentially think about climate change and have the right adaptation and mitigation measures, we have the opportunity to make this like a less warming scenario than if we did nothing. So that's what one thing you can take away. But interestingly, like this is kind of like a collection of mortgage portfolios across the portfolio assets across the US. And you can see many of them are based in California. And if you wanted to study the asset level risk across each of these portfolio elements, you can then go into those climate models, look at the representative model outputs, and then ensemble those results, and then come up with a heat map. So it's relevant because in California in the last year, you've had the last multiple years, you've had so many wildfires. It's kept the fire and rescue team incredibly stretched, and it's created a tremendous amount of economic as well as social damage. And you've probably seen some pictures in like September. This is how the sky looked like at 11 a.m. in San Francisco. It was just like orange. And it's a sight that many of us had never seen. And it's indicative of like the wildfires that were happening in the neighborhood and the smoke flowing closer to the bay. And if you looked at the risk of the different assets in that portfolio and you sorted them by their risk exposure, then you see that the riskiest assets are pretty much in Southern California and parts of like the Northeastern US. And what you see in yellow are like the close to no risk kind of situations. So Through that, you can aggregate the vulnerability across those portfolios, across different types, and look at risk groups over assets. And then you can get to estimated loss distributions across different types of assets. So the key idea here is you've gone from a portfolio to essentially understanding across different kinds of assets what the risk is. And that helps actionable insight in terms of funding mechanisms and in terms of new kinds of build-up, in terms of loan underwriting. And that's kind of where decision-making around climate adaptation often resides. So that's kind of like the workflow we are trying to get through climate adaptation measures. And I just want to go back to asset level geospatial analytics. You know, everyone thinks it's all about data. It isn't. So in order to make meaningful functional capabilities that can influence the world today in terms of the decisions that we all make, you need a combination of spatial inference, machine learning and data, you need interpretable metrics that can be communicated to a broader audience, and you need the right kinds of interaction design. So those are the things we are focused on at Sust Global. And I'm happy to field any questions. Feel free to reach out. We're always looking for smart talent to join us. We're like an early team of scientists and commercial folks. So there are tons of open roles we're actively hiring for. So how do you want to do this? Lainey, do you want me to?
Yeah, thanks so much for your talk. And I especially appreciated that point at the end, like actually having data be actionable is a step that is really important. And some folks in my PhD program who are working on that really had a lot of work cut out for them to take the climate science models and communicate it in a way that whoever they were talking to was really going to be able to use it. So that's a great point. And yeah, let's take one question for Gopal if there's one that someone wants to jump in with, and then feel free to keep writing other questions in the chat. And then Gopal, similarly to Erin, you can just respond to a few of them in writing in the chat as we get to the last panelist. So anyone want to just ask a first question to Gopal?
I can ask a question if no one else.
Go for it.
I was just curious to know, you had a flood, you're looking at buildings that are growing out laterally, and you're using a flood risk area to determine vulnerability of those buildings. I was just wondering if that flood risk map, is that a static map or does it get updated regularly?
Yeah, great question, Aaron. I feel like there are a ton of providers of flood risk maps, and that's kind of input into loan underwriting or like insurance underwriting in many regions. So it depends on the region. So some areas they're updated. This one, for example, that we used was updated every year. So that's kind of the periodicity of updates. And again, now with the changing climate, you kind of probably have real-time inputs into that. So I would say it varies, but you can expect an annual update.
Gotcha, thanks.
Cool.
Any other questions before we dive into Anthony's presentation?
Yeah, and feel free to keep writing them in the chat if it hasn't. Oh yeah, Bruno, do you want to go ahead and ask that and then we'll move on?
Yeah, I'm not sure my question is completely clear, but basically when you do that analysis on different assets, and I'm thinking about real estate here, you will identify assets that are at risk. So there are a number of reporting schemes that exist. So I'm thinking of GRESB because I know it. But can that information be used by asset managers to be able to report some of their assets as at risk or even strained assets?
Yeah, absolutely, Bruno. I think that's like a target market we're actively addressing, which is the GRESB kind of reporting. And asset managers really need these kind of tools. So that's kind of one of the verticals we're serving.
Okay, lovely. Well, let's turn it over to Anthony, and and then we'll open it up for a general discussion.
Great, and I just want to ask one question. How technical is the audience? Just like the backgrounds people are coming from? Is it a pretty big cross section, or?
I think it's a pretty big cross section. I mean, some people have very technical backgrounds and very data science focused in their careers, and others are coming at the climate problem from other aspects. I mean, I would guess for this talk, it's maybe more of the technical folks in our cohort, but I haven't like closely analyzed everyone who's here. But yeah, it's pretty diverse. And so, I mean, any like acronyms, let's just define them, and you know, people can jump in with clarifying questions if they have any. But yeah.
Okay, great. All right, excellent. So let me share my screen here, and so I'm going to give. I guess the way I thought of doing this is just to give to sort of take you through like a specific example, like working with one customer segment for us. So so ClimateAi, I mean, the work that we do, it could impact many different industries, like from agriculture through timber and natural resource management, as people have mentioned, sort of, you know, real estate and energy, and there's a lot of other groups. So as a company, we decided to focus on agriculture after doing a bit of an exploration. And then within agriculture, I'm going to use a kind of presentation that we often leave behind with customers in the seed category, just to give you as much of a kind of concrete, maybe, you know, understanding of sort of where this where the rubber meets the road, I guess. But seed companies are a really big sector for us. We are also working a lot with processors. So if you think about people who are maybe a processor for potatoes, right, who's going to work with a ton of growers in some region to produce potatoes, and then is going to turn those into, you know, chips and French fries, et cetera. So that's another, you know, potatoes could be one, but we have rice. There's a few other categories like that. And then we also do a bit of work with ag investors, the finance side of it. So people who are buying land or also lending into it and are thinking about their risks that way. Okay, so I'll just jump. So just the quick background there. So the company, ClimateAi, was started about 4 years ago out of Stanford. Max and Himanshu are the founders. We have Himanshu's from India. He led modeling out there for the Indian government. And then Max is, he grew up in Ecuador, and his family does industrial scale pineapple farming. And then he went to Harvard, did applied math, and then they both met at the GSB, doing kind of a joint program with the GSB and also the Earth system. So, and I kind of mentioned that just to show it's like there's a really diverse group that we've got different backgrounds that people are bringing in. For us, our expertise and where we've gotten a lot of value is being at that intersection of, you know, we have climate scientists, a lot of people like with PhDs, postdocs, et cetera, in climate science. Then we've got data science, and we've also got the ag side. And by bringing all of those together under one roof and then going super deep into ag, that's really where we've been able to make a difference for customers and not staying at like a superficial sort of higher level. And I think that that might be something you see in a lot of areas of people working in climate, is like, you know, when they're going for a specific segment, if they can really understand that problem and then figure out how to apply it there, I think they see a lot of value, because there are tools and people that are trying to just do things at a much higher level or provide a sort of broad stroke kind of tool that could work with any type of asset or something. And I think that ends up being pretty problematic from what we've seen. So the company, though, the key insight and what was interesting when it got started was basically climate forecasting. And I'm sure some of the other panelists, you know, they sounds like they use climate forecast and some of the models that are coming out from the different government centers. So right now, it's something that is basically only done by government agencies. So the people who do the climate forecasting, they're typically, you know, you've got NOAA in the US, you've got the European Center, they have teams of hundreds of scientists, and they're basically modeling all the physics of the interactions on the atmosphere and the oceans and the you know, land surface models and things like that. And so they're really complex models that have to be run on supercomputers. And so they only release data, you know, new results probably once a month, because it takes them a few weeks to run the model and it costs millions of dollars, and then they've got a new set of results. So the interesting approach to this that ClimateAi took was basically applying machine learning and looking at climate as an image, and then starting to bring a lot of like computer vision techniques into it. So when I say that, I mean, you could literally picture the surface of the planet with like grid cells drawn all over it, and those are your pixels now. And then instead of the fundamental components being, you know, red, green, and blue, they're temperature, pressure, and wind speed. And then you're, you know, at that point, you're off to the races, starting to, you know, instead of detecting a pedestrian that's walking out in front of the car and figuring out, is it going to go left, is it going to go right? In this case, it's a heat wave that's, you know, starting up in one area and then might impact another area. And so I think we're the first private company to actually have our own climate forecasting engine that we can run like this, and we were able to beat the European Center at forecasting things like El Nino and some others. And then the real beauty of it, though, is that it's lightweight. We can run it on a laptop and 2 GPUs. So the flexibility is actually what's sort of opened up everything interesting that we're doing here. And so just to give you a high level, I mean, sort of the old way of doing things is like people just looking at a weather forecast, and they are traditionally using historical averages for most of their planning. So this means they're taking a 3 or a 5 year average. To stick with that potato example, right? The processor might say, okay, well, I've got orders. I need this many potatoes to fulfill my contracts. So, you know, based on the average, you know, number of, you know, pounds of, you know, potatoes that are produced per acre, this is how many acres I need of the different varieties, and we're going to grow them. Okay, and that's kind of how they make a decision. And the problem is that these historical averages have gotten increasingly bad at, you know, predicting the future and what's going to come. And so the variability is just going way up as a result of the shifting climate. And that's really where ClimateAi focuses, is trying to help people understand how weather like fundamentally is impacting their business and how it's like driving the variability in the results, and isolating that piece of it, and then creating forecasts that are actually looking at the impact. So we're really like impact modeling for the business. So instead of it just being some forecast, it's what does that actually mean for the crop and the specific varieties that I'm growing on these farms in these regions. And then given the forecast we have today, and, you know, with all the uncertainty in there, how do I optimize the decisions that I need to make at this moment using the best available information, rather than just defaulting to a historical average. And so we work at a range of timescales, everything from the short-term weather kind of side of it, of days, you know, looking at a week out kind of thing, all the way through months and like across the season, and then all the way through, you know, decade-old forecasts that are looking out, you know, much farther into the future. And so I think I hit most. So again, we're integrating business data, you know, from the customers that we work with. We obviously have the weather data and then all the modeling to create these forecasts, and we can do it globally. We can do it from a regional level down to a specific farm, a specific asset, as people were talking about earlier. And our goal always is to bring the lowest uncertainty that is scientifically possible to forecast the parameters that the customer cares about. And oh, and just my role here, if it wasn't clear. So I lead product and growth. It's basically, you know, I'm focused on commercialization and new markets. So a lot of it is sort of the intersection of, you know, what's possible, understanding the customer need, kind of trying to go 0 to 1, and working with the data science team on, you know, what we can actually deliver, and then try and actually execute, ramp that up, and then kind of bring that into new verticals. And just to give you an idea of the like sort of overall technology stack. So I mentioned that first piece, which was the first piece on the left, the top left there, was basically, that was what we, you know, the work that happened at Stanford that sort of put us on the map. We had this breakthrough. It was pretty interesting because it was also doing transfer learning from all of the like simulated, you know, thousands of years of climate data, and then transfer learning and applying that on the actual observed data, because we actually don't have that much historical climate data. You know, we've got 40 years of probably observed history, and if you're getting data once a month out of these global climate centers, that's just not that many data points to actually apply, you know, machine learning to. So that was the first thing. Then we got into sort of that modeling, looking at the impacts on specific crops. So this is a little example of us forecasting strawberry yields about a month or 2 months out with incredibly high accuracy. And we went from there. We did the long-term piece. And so the long-term, I think what's sort of interesting to highlight there is that you have these global climate models that are you know, coming out of all of the different agencies, and they're not all created equal, right? I mean, everybody is building them and tuning them for different things that they care about, right? So the Europeans are trying to focus on what's going to impact Europe, you know, broadly, right? And India's got theirs, and they're focused on different oscillations and stuff that would impact India. And so they're all better at forecasting different things and in different places. And so unfortunately, when they make a lot of the long-term reports and they say, here's what's going to happen for the future, typically they just average all of these models, which is actually not, it doesn't really make that much sense when you start to think about it, because they're not all created equal, right? Some are better, but it's not PC also to like say one country's model is not good at doing a certain thing. And so they end up in this weird thing where averaging is like the only sort of acceptable answer for this. And so what we do is like a dynamically, we dynamically weight them. So it's an intelligent weighting that's based on what did the forecast say, and then what was observed, and then using that to actually assign weights across all of them to create a forecast that ultimately has a lot less uncertainty in it. And so now it can become a lot more actionable, because I think as you're all sort of setting off on, the work in your careers here in climate, one of the big problems is that if the uncertainties are really huge for the future, you might have two totally different potential actions you would take as a possible outcome. And that's not really that useful to a customer. So trying to narrow that and really hone in on what's going to happen in a specific area is really critical. And we did a similar thing with short-term weather, basically to get more accurate short-term forecasting, which again, has proved quite successful. And then the couple other areas we use machine learning that are just might be interesting to the group are, we do a bit of crop stage monitoring and like drawing out the growth curves basically in season. And this is a combination of, it's an unsupervised learning approach using imagery. So this is one of the first places we actually use imagery the way people traditionally think of it. And so it's just taking satellite inputs from many different types of satellites. So it's very redundant, and then, and it can deal with clouds and things like that. And then using it to kind of fit a growth curve and estimate the cycle. So you can do that in real time. And if you imagine in an ag space, being able to see at a glance, what is the state of the crop across all of the areas where I'm growing it. I know the weather to date, so I have some idea of maybe how that's impacting the yield or the quality or something like that. And then with a forecast coming up that's now really targeted to their business and is more accurate because of the way ClimateAi does it, you can bring that all together to really say, okay, well, here's what we think the timing is going to look like, when the crop's going to be ready, and the order and the impact on the, like I said, yield, quality, things like that. So that's like kind of high level, a lot of the different tech pieces that we have. I could dive into a lot more of these, but I want to make sure we leave some time for questions. So I'll probably cut it there, but happy to talk more about sort of any of this and go farther.
Yeah, thanks so much, Anthony. That is fascinating and a lot of food for thought. And we do have a lot of folks interested in the food and ag space related to climate. So I think there should be a lot of questions around that. Yeah, zooming back in here. And one of my questions, just in the sense of like using this higher data quality approach to planning and like all across the ag supply chain, if you're, just getting used to that, like maybe 20-year mindset instead of a 1 year or 5 year planning time frame, and you're in a place like the West Coast where fires are just an increasing risk in the fall, are you like able to have conversations based on these data tools around like, oh, should I consider planting earlier or harvesting, like ways that farmers can mitigate that projected climate risk for their area, whether it's harvesting hopefully before the fires hit, or like, is that something that feeds in at all, just because it's been so recently on so many growers' minds in the West?
Yeah, I mean, I think specifically for us, it's not that easy to work around fire. I mean, it's very hard to actually forecast, fire. I mean, you can look at kind of fuels and dryness and things like that.
Yeah.
I think that the biggest thing is that the fires and also the COVID situation have really put a spotlight on resiliency and the need to be able to maintain your business's productivity irrespective of shocks to either the supply side or the demand side. And that's really put that at the forefront. I think that's just sped up conversations where broadly all of our work fits into that, of like, how are you going to respond to potential shocks to the system? And is your system really fragile, or is it something that's actually quite robust? And so I think that that's more how we've seen it factor in, and they try to plan around the weather and everything. But the fires specifically, a lot of it is just like, get the crop out of the ground as fast as you can if you have time, if you think it's coming in there. Otherwise, I mean, with vineyards and stuff though, grapes are getting damaged from smoke. They get smoke taint, right? And so if you could really accurately forecast the impacts of smoke taint on wine grapes, you can make a lot of money getting out there on the spot market contracting grapes and knowing which ones were before the testing basically came out, because then the price goes up hugely, so you can make a nice return. If anyone has a lead on that, talk to us. We could explore a project.
yeah, that would be certainly amazing info to have. Okay, let's see, Bruno, you want to go ahead and ask your question, and then we'll take a couple, like 1 or 2 specific to Anthony, and then anyone who had a question for anyone or all of the panelists, feel free to put a +1 in the chat and I'll call on you.
Yeah, so my question is about so being able to see climate impact at a very local level. could you also model what would happen if we did something? So, for example, I was thinking about the Bay of Bengal along the coast. Could you identify the best places to restore mangrove along that coast using your model?
Yeah, that's an interesting question. I think that as long as there's a good sense of, what is the impact or the benefit that comes from taking a certain corrective action, then you can say, okay, well, what would that likely mean for the, overall risk in the portfolio of production or something like that, that you might have if you made these changes, right? So there's a lot of people that are trying to say, hey, I work with all these producers or something. They're all doing different things. And we can identify if you're taking certain actions, what does that actually mean for the resiliency, right? We can kind of score, if you have a measure of something, to then score that and say, well, what does that do overall for either the farm or that a portfolio level, the resiliency of your production, your supply chain there. And so I think the big question would be with the mangroves is just, is it well understood, sort of the impacts that you get from that and sort of how to model that. And then you could factor that in to basically, you're just doing an optimization at that point, I think. So that's my sort of high level answer, but I think the details are probably where it gets a little bit trickier.
Mm-hmm. Yeah, thanks for that response. Let's see, anyone else? I'm sorry if I missed a question from up above or anything like that, but feel free to bring them back up or ask new ones. Yeah, let me know.
So can you figure out which land specifically in a particular area is going to be least impacted by fires or climate impact? So like, I mean, could you identify some piece of land that somehow is going to miss, like when there's a big fire, is not going to be impacted as much somehow?
Yeah, I mean, so extreme risks. So I didn't mention this too much on the presentation, but like forecasting extreme risk is really critical, right? So there are things you can look at and say, okay, well, if the averages are changing by a small amount, by a degree, let's say, what does that mean for the risk of an extreme heat wave that's over some threshold? And even small changes can be a very large impact on the risk of an extreme. And so we can use the forecast to then sort of disaggregate a longer term forecast to then break it up and say, okay, what is the risk of this extreme event that you're interested in? However, there are certain extremes, like some of the stuff people care about, a hurricane, a wildfire. I mean, those are very, very hard to forecast. I think what's a lot easier to say is, if we're looking at a long-term trend, which areas are going to be increasingly suitable or less suitable for a certain type of production, and what is the probability and the risk of experiencing certain extremes. And then when you look at that over time and with enough years or enough locations, yes, you can do that with your probabilities will be right. You'll be wrong in some spots, but you'll be right more often than not. But specifically, if we were to say, could you avoid buying a property in this spot because it's less likely to get hit by fire? I think probably at that point, you're a lot better going super local. Somebody really knows the area and figuring out how to just looking at where the fire is going to track on the ridge and things like that. And probably those local features are the most important thing. That would be my guess. But we could definitely say what's the risk that, you're going to have temperatures and dryness, et cetera, that would, facilitate that.
Yeah, great question. And thanks for that response. Ritesh, we'll go to you and then Keisha.
Thanks. Yeah. So my question is for Aaron. You kind of mentioned how your models can kind of apply to places without ground truths, and I'm curious, what are the challenges there, how well that works, and if you run into any issues with that. And I guess sort of a second part to that question is for anybody on the panel who wants to take it. Machine learning in different domains has different biases that we've kind of experienced over time, how that affects whether it's facial recognition or voice, voice speech to text kind of thing. So I'm curious if you run into any interesting weird biases based on data in this climate related domains, because I'm not really sure how that would manifest itself in this domain. I'm curious if you run into anything like that and how you handle that.
So, okay, I'm going to start with the second question and work back to the first one. So I'm not like I said, I'm a remote sensing scientist, not a data scientist, but some of the biases that the machine learning people have talked about is actually with satellite data, because some of the satellites acquire data at a certain time of the day. So a lot of the models are trained on that specific time. So then that can create a bias of like mainly morning. Like you're trying to predict emissions in the morning, but then what do you do when you're trying to get in the afternoon? So we're trying to remedy that with other sensors that can like then help train the models to account for this morning bias that is occurring. That's the extent of my bias with it. So I would feel free to email me if you have any questions about that. The first one is how to do it with ground data, like areas without ground data. So, I mean, the whole point of comparing where we have satellite data and ground data with the modeling is to create as robust tool as possible that can just be applied to somewhere else. But we're always looking for collaborators and people that are willing to share ground data in areas that we don't have it, in order just to vet and to make sure our approach is correct with estimating greenhouse gas emissions. But from a satellite perspective, you can also treat satellite data as, in a sense, in situ ground data, depending on how you use it. So in some cases, if we use that as a way to get a sense of what's going on in a location without that specific ground data.
So, sorry, can I, that was my question. So, and the reason why I was asking is because I've worked with air pollution data, some satellite data, some like ground-based model data. But I know that like the satellite models are trained on some of the ground-based observations, but like we can't apply those to Africa necessarily. I mean, they get applied to Africa, but like they don't work that well. So I was just wondering, like, if there was, I guess, something I didn't know, like some clever trick that people were doing in order to make that work.
I was going to ask you, do you know the secret handshake or clever trick? But I mean, no, I mean, those are things like, you know, some of those models you've seen in papers now, they're trained on, you know, United States or Australia or Europe, but then when you switch over to a country in Africa and or South America, you get errors associated with it. So there's some things that need accounted for. Currently, we are working on that and looking at those too, well, also, by reaching out to collaborators too.
Right, and then how do you deal with like, I mean, it seems like you guys get data pretty quickly, but like, do you have the same issue with aerosol optical depth, like if it's cloudy, for example? I mean, that's just, I know that's maybe more of an issue for air pollution than other things. But.
Yeah, I mean, clouds are of course an issue with optical infrared, but my background is radar. I use STAR, like Sentinel-1, for most of my research. So the question is like, can you use that as a way to do some type of indication of emissions? And of course, radar does not measure emissions because of the wavelength and everything, but can you use it to look at, you know, activity in some factory based on machinery, things like that, or some type of other indicator that can be linked then to the emissions data. I mean, so there's other satellites there that cuts through the clouds, but then you have to do an extra step of trying to link it to something meaningful.
And I'll just add as a 2-second thing that we spend a lot of time doing bias correction after the fact. So especially like in our case, we do an unsupervised learning approach. So the bias doesn't come in, you know, early on with the way that, you know, let's say you're labeling the data set or anything, but what you ultimately end up with is something that needs to be shifted around at the end. So you've got a good sort of objective measure, but then as far as what does this thing that we are detecting actually mean as far as what you see on the ground? And then when we get that adjustment factor, then we can kind of shift everything and we can make it a lot more accurate. And that applies as well to forecasts and temperature and things like that when you want to take into account, you know, sort of local variations in a microclimate or something.
Right. I mean, like another question I have is like, how much does it matter? Like, so for some of the air pollution stuff, like it's frustrating that you don't have like detailed information on the ground for like everywhere, but in some cases it doesn't necessarily matter that the data is perfect. Like, I don't know, I'm guessing that for other things like climate projections, like it must matter quite a bit.
Yeah, I mean, I feel like that all depends on the customer, right? You don't need to go overkill, but you need to get to good enough to be meaningful where you're going to have a real ROI, because you're trying to get people to change their behavior, right? So you're trying to move, like, what is that bar? So I know what that bar is for us and for all of our customer segments, but I know, Aaron, do you ever have people coming back to you and they're just like, you know, this is too, yeah, you're going too detailed, this is too much, like we don't.
Yeah, I mean, we're working on multiple levels of detail, but yeah, we're trying to figure out what detail to go at. Like, is this like just do like a city level? Is that good enough, or do we need to go really down and find detail? So it depends on the impact we want to try to make with it.
And the
So yeah,
sophistication, right, of the probably the person you're working with. I mean, because that's, I think it's very important for everyone to remember that like the wider world out there is using very crude tools to make very important decisions right now. And so the state of the art might be a very low bar. That's a good place to start. There are people even for us that we could sell to that are far more sophisticated, but like, why would we start with them, right? They'll be the most demanding customer, and you know, you can work up towards that, but yeah, the world is not being run with like, you know, super advanced, insightful ways of doing all this stuff. It's just kind of not how it works.
So, like just to continue, some countries are just starting to get into remote sensing as like the last couple of years. Like there's a whole UN NASA training to get sustainability goals to actually get countries to use some of the free data from these from NASA to help inform. Like some countries still you have to order the map, which is, you know, printed by hand, and it has to be geo-referenced and everything. So there's a push trying to get countries to use more of this information. So that's like a starting point with some of them.
And I saw a quick question here about locusts. I'll just flag that. Yes, we haven't done this, but it's come up, and basically if you could tie it back to the climate and the weather, then you have a shot at doing this. And so we do look at forecasting risks of pests and diseases and how that's going to change as the climate changes and what that looks like both in season and longer term. And so I think the germination cycles are related to temperature and a few other things that are pretty critical here. And so you could look at how that risk factor would be going up and up over time. And then what's the likelihood of having a big outbreak, which I know has been, you know, decimated places like Kenya and some others right now.
Yeah, that's cool to be able to use that for that. So we are just past time a little bit. So I'm just going to ask that if anyone has a question that didn't get answered, you can just share it with me maybe, or put it in the chat and I'll save it. And if it's okay with the three of you panelists for me to just send you an email with like any 2 or 3 lingering follow-up questions, I'll just do that. But yeah, does that sound okay?
Sure. Yeah, and then the same thing I think the other people said, you know, we're hiring. We also take a lot of, you know, we take interns, we do all things like that, and we're kind of ramping up. I think we're hiring on basically every single team right now. So if there's something that interests you, or maybe a collaboration, anything like that, we're also very, we like to work with others and try to share things. That's kind of in our DNA. So yeah, please keep us in mind.
Yes, ditto with ClimateTRACE and everything. Collaborators, people that are interested in working, you know, feel free to reach out.
Yeah, and is it global in both of your cases or all of your cases, or is it mostly hiring in the US or collaborations in the US? Just because our cohort is global.
We are remote right now, so I imagine we are global in terms of organizations. In terms of specific walk time, I think it needs to be within CONUS, but you know, I think everything's negotiable during the COVID time.
Yeah, we're pretty global. We've got team members in Europe and South America and Asia, things like that.
Cool.
Yeah, same here, remote and global. You have to be friendly to those two in the times of this pandemic.
Indeed.
Yeah, we could have a whole different call on how to manage these time zone issues with your teams, which is its own.
Yeah, exactly.
Can I just ask one question? I actually look at all your website, right? And I have no idea of what kind of software or technology stack you actually are using behind. And so I don't know, do you have a need for software engineer, or is it more data engineer that you want?
I can speak quickly. Software is huge because that's ultimately the interface then that it plugs into. So the first was the data pipeline and everything, but then the software has become a big focus. It's a lot of Python, Django. Python plays nice with all the, you know, data pipeline tools that we have. But yeah, it's a lot of, you know, Python, Django, JavaScript, a couple other tools, sort of whatever's needed for the job. But those are the big ones for us.
Yeah, for the most part, us too. Python, cloud processing, Java, things like that.
Cool. Okay, well, so I think a lot of you shared your emails at the last slide or something. So I'll maybe also just follow up, and if it's okay to share some of those slides with that contact info, I'll post that in our group community channel. And yeah, I look forward to any follow-ups and things that stem from this. But it's been a fascinating hour and 5 minutes, and I've really learned a lot. So thank you all for your time.
Thank you.
Thanks for having us. Appreciate it. And I just stuck my email in there to a couple of people who replied to me. I think the whole chat maybe can see it now too. So yeah, feel free.
Yeah, awesome. Thank you all.
Thanks,
very
everyone.
much. Take care.
Okay, bye-bye.
Bye.